Bismillahirrahmanirrahim. Today I wanted to talk about a very interesting question, what I call the house on fire question. This is not it actually, it's the question that I'm going to talk about after this question. But this question that's I'm presenting here first is an example from your textbook, and I'm going to read it for you. It says, suppose you are going to shop in the store B. So this is supposed to be a shopping mall, and you are shopping here in store B. So you're going to shop over here in this particular store, and you're going to do then what you're going to do is this. So suppose you're going to shop in store B, and then return to your car, and then go to store G. So what you're going to do is you're going to shop here in store B, then you're going to return to your car, which is parked over here. It's supposed to be a parking lot, and then from here you're going to go to store G over here, because presumably you have stuff with you from store B, and you don't want to carry it around. So you're going to get out of here and go to this parking spot. Maybe that's where you parked your car, and then you're going to go there to store G. So that's what it says. So you are going to shop in store B, return to your car, and then go to store G. The question is, where along the line S, so this is line S, where should you park over here? Should you park over here? Should you park over here? Where should you park your car so where along line S of the parking spaces should you park to minimize the distance you will walk? So the question is, you don't want to walk a whole lot, right? Because if you park, let's say over here, you have to go all the way from here and then go to store G, things like that, right? So what's the shortest distance, cumulative distance, that is the total distance you would have to walk, if assuming you don't want to walk too much, from here to here, and then store G, because parking at different places would imply different distances to your destination. So if you parked over here from B to this parking spot, and then from that parking spot to G, that's a different parking distance than the walking distance than if you were to park over here and or then go over here. So the question becomes, what's the shortest total distance that you can possibly walk if you did not want to walk too much? Okay, so that's the question, and it's a tricky question actually if you don't quite see it, and it must have to do something with reflections, right? Otherwise, why in the heck would you have this question in this particular section of the chapter? So, and that's what it is. So the question here is like this. So the key to understanding and doing this question is the following. So let's say here you are, and this is your house, and you wanted to go to the post office, which is over here. So this is your home. Let's call your home at point A, and that's the post office. And let's just label that as post office. And you wanted to mail something very important at the post office, and you're going to go home, and you're going to go to the post. You're at home. You're going to go to the post, but then you talk to your friend. And your friend says, hey, I have something important to mail also. Dan, can you just pick it up and mail it for me? So let's call your home point A, let's call post office point B, and let's call your friend's home point C. But then you say, man, I'm like in a hurry, because I really got to get this mailed out like ASAP. And if I stop by your home, it's just gonna, I'm gonna have to go first to your house, and then I have to go to the post office. That's gonna be a longer drive for me. So, clearly it's gonna be a more longer distance, right? From going, and the shortest distance between any 2 points, of course, is a line. It can here in this case is segment. The shortest distance between A and B is a segment. But then you say, well, I don't have that much time. But your friend says, no. Okay, this is what I'll do. I'll just meet you here at the roadside right there, and you just stop by the car, and then I'll just wait for you right there religiously, and then you just come to me, and then I'll give my letter, and then from there you can just go on to the post office. I said, that's cool, and then I don't have to do any extra driving then, right? So the point being that if 3 points are collinear, in this case A, C, and B, that's going to be the shortest cumulative distance between A to B. It's like two baby segments give the one big segment, right? So the shortest distance between combined distance between AC and CB is if there are all three of them are collinear. And that's the idea over here. So what one has to understand is, if you want to point somewhere over here, the shortest cumulative distance, so you want the shortest cumulative distance between A and then whatever this point is, let's call that point P and G. So you want this segment plus this segment to be the shortest among all possible segments, let's say from here to here, when you add them up. So the shortest distance would be as if P was on that segment. So while P is not, obviously is kinked like over here, you know what I'm saying? So how do we go about that problem? The way we go about solving that problem is like this. So what you do is you reflect B, this point B over here, across this line S. So what you do is you draw a perpendicular, because you measure distances from a point to a line by their perpendicular distance. So you draw a perpendicular over here, right? And then you draw an identical segment length. I'm going to try to find the identical segment length here from right here to on the other side. So I'm going to basically reflect this. So if this point is B over here, this point is going to be like reflection of B, or B prime. That is, this segment length is the same as this segment length. Okay, so in other words, if you were over here, and if you go travel from here to your car, that's the same distance if you were to travel from there to your car. They're equidistant. Okay, so fine. And then what you can do is a nifty trick. Okay, then you have this point G over here. Then all you do is you connect point B to point G, because the shortest distance between point B and point G, B prime and G, would be a straight line like this. And then the intersection of this segment B prime to G right here would be the closest spot, the shortest distance, combined distance between here, because these two distances are the same. For example, if you were to go from there to there, okay, so that distance is going to be the same distance as this. Now it doesn't matter if you walk from here to here or if you walk from here to here, so those distances are the same, so it doesn't matter which way you walk, right? So, and if you go from here down here and there, it's the same thing as going from here to here to here. Let me repeat that again. Going from this point to this point to this point, okay, to making a V like this, okay, is the same distance as going from this point to this point to this point, because these two segments are of equal length, aren't they? So making a V going from B to G is the same thing as going from B prime to G, isn't it? Right? And you can see the shortest distance would be from B prime to G. Correct. So the shortest distance that you can make between B and the parking lot and G would be this point right there. You can call it P. All right. How do you find this point? First, you have to reflect B across this line S. So you reflect B across this line S to find B prime, and then you make an imaginary line from B prime to G. And you park your car right here, probably like over there, and that would be the shortest distance that you could go from this shop B to parking space P, and then you go to G over there, and that's how you go about finding this point. Now, by the time you go over here and measure the distance and reflect it upon B prime, and then park your car over there and then go over there, you probably walked twice as long as you did anyways. It's a pointless exercise in that sense, but it's a good intellectual exercise, and maybe you'll get a few steps in there. So that's how you solve this particular problem. And as I said, this problem is the first of the two problems I like to share with you. The second problem is actually the same problem stated in a slightly different way, which I think is actually more fun. Okay, so here is the question. So imagine this tiny little house over here. That's like your house over there. And imagine that's like your neighbor, and you see the neighbors, like there's a little kitchen fire going on. There's like, oh my god, this house is like on fire. So, and then it so happens that you're lucky because there's like a river that runs by your house like this. So what you want to do is you want to like take a bucket and you want to go to the river and pick up a bucket of water. This is like the ultimate bucket of water. So you take the bucket of water and then you want to go to the house over there. And you know, how you going to do that? I mean, you're in a hurry, obviously, because you know you want to be like taking the shortest distance from the river to that other burning house. So if you go from here to, let's say, on this point over here, and then over here, that could be longer distance than from here, let's say, to this point over here, and then you go over there. So the question is, what's the shortest distance from your house to that burning house, stopping at the river? Stopping at the river. So where on the river do you stop to minimize the distance that you have to travel from your house to the other house? Well, this is the same exact problem, actually, but it's kind of more fun because there's a sense of urgency over here. You know, it's not like you go into a parking lot in your car, right? So here you have to go from your house to the other house. Again, this is a question about reflection. So what you do is you reflect the distance from your house to the across the river. So what you want to do here is like go from your house to the river and to the other house, right? To find the shortest distance like that. So what you do is you reflect the distance from your house to the river, and it's a perpendicular distance because the shortest distance between a point and a line is the perpendicular distance. So you reflect this, and this would be like the B prime, like in our question over there. So it's like B prime. If this was B, and this would be the B prime. And then you connect the B prime to the house, and that will give you precisely what this particular point has to be to get to the house from the shortest distance. Okay, so this is a beautiful question, the shortest distance between 2 points, stopping at a third point. Okay. Now, if this question was given to you on a Cartesian plane, let's say if you wanted to go from point A to point B, but it's stopping, let's say, somewhere on the x-axis over here. So if you wanted to go from A to C over here like this, what would be the shortest distance stopping at the x-axis, so to speak, between, would that be this point, or would it be this point, or would it be like this point over here? So as you can see, if the x-axis here, for example, was like the river, and you wanted to stop on the river on the x-axis before you go to point D, the question is, in the Cartesian plane, how would you go about finding this? So this is again the same question, like if you wanted to go from your house to the river. So you would take your house and like over here, and you would reflect it across over here, and then simply you would just take this point, the reflected point that's in point over here from the house, and then you just connect that, and this would be the shortest, that would be the point where you would have to stop on the river like that, because these two segments are going to be congruent, and so taking this route or taking this route is going to be the same. So the same analogy would apply over here, actually. So let me just get rid of this yellow point here. The same analogy would apply. So here you would reflect point A across the x-axis because that's where you're going to stop. So here we go. If you reflect, I made this easy because this is like on the y-axis. So this would be like A prime, and I just reflected this from here to here. So and then I just connect A prime to point B like this, okay, and then I would have to simply find the intersection of this line. So here you would have a ordered pair x1, y1, and here B would be like x2 and y2, and of course you can then find the equation of the line that contains these 2 points. So once you find the equation of that line, if you remember, if you're given 2 points, you can find the equation of the line either in the y equals mx plus b form, or in the slope other point slope form, like this, x minus x1, excuse me, so x minus x1. So once you find the equation of this particular line, then you can find the intersection of this line and the x-axis like there. That is, you can find this ordered pair, because this this line, you just have to substitute y equals to 0, which is the equation of the x-axis in there. So you can find the intersection of this line and the x-axis, and then that will give you the point that you would have to go to if you wanted to go from A to B in the shortest distance. So this is, I think, a very beautiful question, and which tests our understanding of reflections, and you can see how you can use it to solve some nifty questions and perhaps help save lives. Until next time, assalatu wassalamu ala rasulillah walhamdulillahi rabbil alameen. Assalamu alaikum.